All right, now moving on to section 1.3 in this paper by Nelder and Wedderburn. The link to this paper and the complete playlist on this paper will be provided in the description of this video. But right now, so what are we talking about? We're finally getting to the definition of what a generalized linear model is. So we're going to combine the systematic and random components that we've talked about in previous sections to produce the generalized linear model. Okay, so we have Z, which comes from that exponential family distribution. We have X, which are our independent variables, and then we've used those X's to produce a variable Y. Okay, and then we are linking that random part. The random part is theta, coming from that distribution of Z, to this systematic part using this link function. Okay, and then they go on to say when Z is normally distributed with mean theta and variance sigma squared, and when theta equals Y, we have an ordinary linear model with normal errors. All right, and so let's talk more about that, and that might help us, kind of solidify what's going on here. Okay, so let me go to my blackboard. So we have our observation Z that have this density function. Okay, Z is the dependent variable. Now the reason I'm writing that in blue and I'm making a big deal about it is because in the past, when you've done like maybe just ordinary least squares, you usually have Y as your dependent variable. Well, and then you say Y is normally distributed, or Y has a particular distribution. Well, the notation here is Z. So Z is what has the distribution, right? It has to come from the exponential family. So, for example, it could come from the normal distribution. The normal distribution, I know you're looking at this and you're saying, oh, that doesn't look like a normal distribution. Well, it could. You just have to rearrange what the normal distribution looks like. And I'll provide, we discussed that previously in this playlist, but I'll go ahead and provide the link to that in the description of this video. Okay, so you can write this to look like a normal distribution. So normal distribution is from the exponential family distributions, right? And other distributions are as well, such as, the exponential distribution, gamma distribution. We'll talk more about other distributions later. Okay, Y equals the sum of beta times xi. So that betas are parameters. We're used to that. Betas are usually an unknown parameter. They could be known, but usually unknown. And then x's are our independent variables. And these are also known. Okay? They're fixed. They're not random, which is the same as in ordinary linear models. You would have x be fixed. So the only thing that's random is your dependent variable. Okay, so now what's new, what we're adding here is this link function, theta equals f of y. So this function of y, that's the link. So this is the link function. Okay, so let's think through this with the example that they said. So they said that when z is normally distributed, so z comes from suppose z is normally distributed. All right, normal distributed with the mean of theta and a standard deviation of sigma, or variance of sigma squared. Okay, and then they go on to say also, so when z is normally distributed, and so you need both these things, theta equals y, we have the ordinary linear model. So let's think that through. So if theta equals y, that means what does y equal? Let me write that. Y equals I equals 1 to m beta I xi. Okay, so instead of writing theta, let me write that. Okay, now this might be looking a little familiar, except you're used to having y written here, but now it's z. Okay, so if I had like an ordinary linear model, okay, so not GLM, I would have something like this. I would have z equals the sum of my parameters and my times my independent variable plus some error term. Oops, a vector of errors. Okay, so this is using vector notation, where these error terms are normally distributed. Right? So this is the ordinary linear model. So what they're saying is this ordinary linear model, right? It says basically if this error term is normally distributed, then z is also normally distributed and then this would be its mean. Right? So the two are equivalent is basically what they're saying in this situation where z is normally distributed. And you have the identity link, which means that the function is just, the link function is just basically 1, right? So that theta equals y. That's called the identity link function.